Welcome to this video on the introduction to graphing quadratic functions, the parabola. Let's begin. Before we get into graphing quadratic functions, let's first define a quadratic function. What is a quadratic function? Well, a quadratic function is a special type of polynomial whose highest power of x is 2. So in other words, if you have a polynomial that has x cubed or any other higher power of x, then we don't have a quadratic function. If we have a function whose highest power of x is just x, then we have a linear function. So again, polynomial and the highest power of x, or the highest power of the variable, is 2. Okay? So the defining characteristic that distinguishes quadratic functions from other functions is that they usually have, they always have this x squared term. What does the graph of a quadratic function look like? Well, it usually looks either like this or it looks like that. And we have a special name for this shape, and it is called a parabola. So it's not a parabola, it's a parabola. And then the last question is, what is the standard form of a quadratic equation? So we usually have y is equal to ax squared plus bx plus c. So notice that means we have a squared term, we have a linear term, and we have a constant. Now sometimes we don't have this b, sometimes b is 0, or sometimes maybe we don't have a c. But if we don't have an x squared term, remember back to our definition, then we probably don't have a parabola. We probably aren't working with a quadratic function. Methods such as factoring, completing the square, or using the quadratic formula give the roots or zeros or solutions to the function. Please note that the terms roots, zeros, and solutions are all used interchangeably. This can be confusing, but they all mean the same thing in this context. But what do the roots or zeros or solutions of a function actually tell us about the graph of a function? Graphically, they tell us where the function crosses the x-axis, in other words, where y equals 0. Graphs of quadratic functions are called parabolas and have the following shape. Notice they can be oriented upwards, so I always like to joke that this is a smiley face, or they can be a frowny face, right? They can be pointed downwards, like that. If you drew a parabola on the coordinate plane, how many times would it cross the x-axis? Take a minute, pause this video, and see if you can figure out how to make a parabola cross the x-axis once, twice, and 0 times. Then unpause the video to see if you're correct. So sometimes parabolas will cross the x-axis twice. So in other words, this is an example of a parabola that crosses it twice, or maybe it looks like this. It could be oriented downwards, right? So that would have 2 real roots or solutions or zeros. Sometimes we'll see parabolas that only touch it exactly once, which means that the vertex lands exactly on the x-axis, or it could be maybe like this as well, okay? But what if it doesn't touch the x-axis at all? What would that look like? Well, that would simply look like something like this, right, where it's never going to touch, because the lowest point, which is the vertex of the parabola, is still above the x-axis, or maybe something like this, where all of the points on the parabola are below the x-axis. Okay, so again, the possibilities are we could have the parabola or the quadratic function intersect the x-axis twice. It could intersect the x-axis exactly once, or it could intersect the x-axis exactly 0 times. So those are the possible outcomes. So let's see what that means and how that corresponds to the results of the quadratic formula. So hopefully you've already learned about the quadratic formula. If not, you can go back and watch my video. So if we have 2 unique real solutions, then graphically that's going to mean that our graph crosses the x-axis twice. Okay? I didn't actually figure out where that would be, so this graph doesn't necessarily correspond to those 2 values that you see there. So again, this is just a rough example. Okay? If you have when you find the square root of b squared minus 4ac in the quadratic formula, if that whole thing is 0, like you see here, right, then that means we're going to have one real solution that's going to look like that. Again, that means the vertex touches the x-axis. Okay, and then last but not least, we might have 0 real solutions. So notice that we have the square root of -5. Well, remember when we have the square root of a negative number, that's really, right, we have to pull the I out. So all of a sudden we have a complex number. So what that would mean is that our parabola is floating maybe up here somewhere or down there somewhere. Again, I'm not recreating the exact graph that's associated with these roots. I'm just showing you graphically where or what the graph would look like if you have no real solutions. It could look like something like this or something like this. Again, it could be oriented anywhere along the x-axis, but it's never touching the x-axis. So those are the 3 different outcomes that can happen. And again, all of the work we've done as far as factoring quadratics or completing the square, using the square root method, using the quadratic formula, all of that work has been to find these points right here. So again, you could have 2 solutions, you could have 1 solution, or you could have 0 solutions. Okay, so you have 2, 1, 0. Those are your 3, those are really the only 3 possible outcomes. Okay, so let's figure out what other pieces of information we can glean if we are given y equals ax squared plus bx plus c. In other words, we're given the equation of a quadratic. So one thing that we know is that if a, this leading coefficient, remember the coefficient of x squared is called a leading coefficient, if that is positive, in other words, if it's greater than 0, that means that our graph is smiling at us. So that's how I remember it, right? It looks like a big smile. Okay, so if a is positive, the graph opens upward. Okay, so it looks like this guy right here, where, if it were to rain, it would, hold water, kind of like that. Okay, if a is less than 0, in other words, if a is negative, then the graph is going to look like this, which means that the graph opens downward. Okay, and again, I like to joke that it's negative. You can remember that it's kind of frowning at you, right? It looks very sad. So that's how I remember that. The equation of the line of symmetry, or the axis of symmetry, is x equals -b over 2a. And if you're like, well, what are a and b? Well, they're just these values right here in the equation, right? So a is the coefficient of x squared, and b is the coefficient of your linear term, your x term. Okay, so we would pull our b and our a straight from the standard form of the quadratic equation. What is the vertex of the quadratic equation, or our parabola? In other words, what is this point or what is that point? Well, to find the vertex, the x value of the vertex is -b over 2a. And then what we have to do is we have to take that number, whatever value that results in, and we plug it in to the function, and then that will give us the y value associated with a vertex. So this says -b over 2a, comma, f of -b over 2a. Now, you might not be familiar with function notation yet. We might learn it in another chapter, but for right now, just trust me, we're going to do some examples. So if this notation is confusing to you or doesn't make sense, just be patient. It will make sense when we do some examples. Okay, and then as it says here, right, to determine the y coordinate of the vertex, we substitute whatever we get for the x coordinate, and then we evaluate it. Okay, the vertical intercept of the graph, in other words, where this crosses the y-axis. Well, that happens when x is equal to 0, right? Well, if x equals 0, this goes away and this goes away, and what's left over? Well, the only thing left over is c. So this is going to be the point 0, c. Okay, and then number 7, as you can see, it says the zeros or roots or x-intercepts can be found graphically by looking at where the graph crosses the x-axis. Then they can be found algebraically by setting y equal to 0 and solving for x.